Gravitation. This video will cover Newton's law of gravitation. The information on this slide can be found in the SACE subject outline, and if you want to go into a little bit more detail, pause the video or have a look at the slides on the OneNote. Every particle in the universe attracts every other particle in the universe based on the mass of the particles and the distance between them. Even if the distance is the other side of the universe, there's still that attraction, but obviously very weak. The force acts on a line joining the center of masses of the two particles. The magnitude of the force is directly proportional to the product of the masses and inversely proportional to the distance squared between them. Now that inversely proportional means that the distance, as seen here, is in the position of the denominator being below the line. So that what that means is when one gets bigger, being the distance between them gets bigger, the force gets smaller. And being directly proportional is when the mass gets bigger of either of the particles, then the force between them also gets bigger. Combining these two relationships, we can come up with the formula as follows here, where the force is equal to a gravitational constant times by the product of the two masses divided by the distance squared between them. And again, the direction of the force is attractive between the two particles. The gravitational constant, capital G, is different to the lowercase g, which we've used for the acceleration due to gravity. The gravitational constant is this value here, and it's a universal constant. It applies in all cases. So if you have your formula sheet handy, just make sure that you can find the formula and that constant on the sheet. So to find the force, treat the objects of concern as point masses, assuming that all the mass is concentrated at a central point in the center of a sphere. The distance between the objects is the distance between the two center points, and the force acts on a line joining these two. Now, going a little bit further into proportionality, meaning finding the relationship between the variables in the equation, if we have a scenario where the force between two objects is given by this formula, then we have a second scenario where for some reason the mass of the first object is multiplied by A and the mass of the second object is multiplied by B. Then because they are proportional to the force is multiplied by both A and B, and it is that much larger. Now looking at the distance between the objects, if the distance between the two objects is multiplied by 2, the distance here, r, is multiplied by 2, but because that is the new distance, that is what is squared. So when we're looking at it in terms of the equation, it looks like this, where this 2 here is the doubling of the distance, and when we square it, the force is a quarter of what it was before. As the distance is doubled, the force is weaker because it's further away, and if it's doubled, the force is a quarter. Alright, now we're going to look at a case of the gravitational force between two objects, one being the Earth and one being any object on the Earth. Okay, so using our formula for gravitational force and also rearranging Newton's second law in terms of acceleration. So we're looking at the acceleration, but because we're talking about Earth, we're going to use the value of g for acceleration due to gravity. We can substitute the force due to gravity here divided by m, which is the mass of any object on Earth, and then we receive this formula here. And notice that because we're looking at any object on Earth, the mass of that object doesn't actually matter when we're talking about its acceleration. And that is why any object on Earth accelerates at the same rate. And by substituting the values that we know, we can find that rate, which is 9.8 meters per second squared towards the center of the Earth. And the only important factors here are the mass of the Earth and the radius of the Earth, and the object itself is irrelevant. So the challenge question for this video is, what will be the resultant gravitational force on an object that is located within the exact center of the Earth? So maybe you can put yourself in the position of being in the center of the Earth, and what forces will be acting on you.